Okay, let's get started, please. So, can anybody tell me what we're doing? Anybody have a sense of what we're doing in this class? What are we doing? Does anybody remember what we're doing? Yes, Jane.
Rational functions.
Rational functions, yeah. So the we're finishing up. So we're finishing up. Sorry, just really tempted to erase this. So we're finishing up so-called algebraic functions, right? We talked about linear functions. Then we talked about quadratic functions, and then we did some applications of those guys. Then we moved to polynomials, and now we're at rational functions, right? And in some sense, it's kind of interesting. But linear functions, although they're the most simple, or maybe because they're the most simple, are the ones that are used most often. So like you have something, and then often what people do, you have something complicated, and then you approximate it locally with something linear. So, right, maybe you have some, something that looks kind of wild, but you're only interested in what happens, near some point. And the thing is that for many kinds of functions, if you zoom in far enough, then it basically looks linear, right? So this is this business of scale, right? You zoom in, right, and then at this scale, it starts to look more and more like a line. These things. So that's something that it's useful to. It's important to understand linear functions for this reason, because you use them to approximate more complicated things. Okay. I'd say that quadratic functions, in the grand scheme of things, are not that important. Okay. Right. Like, it's not like people are going to use quadratic functions. Polynomials, on the other hand, are super important. For the reason that what you'll see in calculus is that many functions that are approximable by polynomials. So if you have something, crazy like this, then it's actually possible to find a polynomial that approximates it, arbitrarily closely. So you can find some polynomial that basically does this sort of behavior. Okay, so it's a way of, these simple functions are ways of getting your head around more complicated things. Okay, that I think, and rational functions as well, although they're kind of less commonly used. People tend to use polynomials for approximation, and not rational functions for approximation. Even though rational functions are actually better. Maybe people don't use them because they're a little bit complicated. In any case, we're finishing up rational functions. Like all this whole section, and the next as well, is to give you some intuition for these kinds of functions, right? And one way of thinking, one sort of attitude is to think of these as animals, right? They're creatures that we construct, and they have their own kind of behaviors, right? And we're trying to get an intuitive understanding of those behaviors. Okay, so one thing we noticed, that we remarked last time, was that if you have something like 1 over x to the n, then it's basically like it looks something like 1 over x squared if n is even, and it looks something like 1 over x cubed if n is odd. Okay. Let me do some examples. So some simple examples. So one was like to graph -2 over x plus 3. Okay. Actually, maybe I'll ask you to do this. So graph the following rational functions: -2 over x plus 3, 4 over x minus 5 cubed, and more complicated, 3x plus 2 over x minus 3. Okay, so take 2 minutes and see what kind of graphs you can come up with. This is, as you see, it's mainly translations and reflections and stuff like that. -2 over x plus 3, 4 over x minus 5 cubed, and 3x plus 2 over x minus 3. Did you all see the meme that I sent out this morning? When your mom calls you by your full name, you know you're in trouble. Did you see that? No. So it's like, you know, there's that sort of meme, when your mom calls you by your full name, you know you're in trouble. Right? And then the mom is saying like, something like x squared plus, like a squared plus 2ab plus b squared. And then, right? And then the kid, who is, you know, a plus b squared, is like, shoot. Okay, talk with somebody nearby to, even if you haven't finished. Okay, so this first one, right? This is what function are we going to relate it to? This is a translation and reflection of, and a scaling of what function? 1 over x, right? So you've got the 1 over x function. You shift it, right? You have the 1 over x function, right? And you shift it over to the left or to the right? To the left, right? So it's, it has a pole at -3, right? You shift it over to the left, right? And it's like this, right? And then you multiply it by -2, right? So the negative, multiplying by -1 flips it over, right? So it gets flipped over like that, right? So right now it looks like this. It's the flipped over and moved over version of 1 over x, and then it gets scaled by 2, right? So it gets stretched out vertically, right? So everything gets multiplied by 2. So I could join this, but something like this. All the values get multiplied by 2. Okay. This one is pretty similar, right? We've got 1 over x cubed, but it's shifted to the right by 5, right? So you've got 1 over x, 1 over x cubed, right? Which is going to look basically like that. And it gets shifted to the right by 5 and then multiplied by 4, right? So shifted to the right, and then multiplied by 5, so everything gets stretched out. Yeah. Okay. How about this one? This one was the tricky one. Did anybody figure out what to do with this one? This was the tricky one because it's an improper rational function. So what you can do is change it into a sum, so that we can use the long division on it that we mentioned last time. And say, okay, let's do long division on it. You could do this maybe just by looking at it, but if you want a system, you could use long division on it. And you say, okay, this is going to be 3, so you get 3x minus 9, subtract, you get 11, right? So this thing, 3x plus 2 over x minus 3, is actually 3 plus 11 over x minus 3. Right, because you've got this remainder of 11. So, the answer is going to be 3 plus 11 over x minus 3. Right? And so, what does that look like? Right? Everything is shifted to the right. So it looks like 1 over x shifted to the right, multiplied by 11, and then shifted up by 3. Right? So it gets shifted up by 3, 1, 2, 3. Right? And it looks like the 1 over x function, but multiplied by 11. So just this taller version, the stretched out version. Any questions about that? That's just using the translations and reflections and dilations and stuff that we mentioned before on the simplest kind of rational functions. Questions? Yes, Manal.
So, from what I'm seeing, is the numerator number that we multiply into denominator?
Yeah. Right, because this 11 over x minus 3 is 11 times the function. Right, so you've multiplied the function by some scaling factor. Right, so all the output values get scaled by that number. Right, like if I have f of x equals x, and I have another function, g of x is 11x, right, then what happens is you take your original function, right, f of x equals x, and then all the y values get multiplied by 11. Actually, let me make it just 3 or something so I can draw it. So all the y values get multiplied by 3. Right, so 1, 2, 3, and 1, 2, 3, and so on and so forth. Right? So you get something like this. Right? Right? You'll have a slope of 3. So the same thing over here, right? You're multiplying this thing by 11, so it gets stretched by a factor of 11. Okay. So yeah. So all this stuff that we did. Remember, we also did asymptotes. Vertical and horizontal asymptotes. All this stuff we did is to do some graphing of rational functions. So, for example, so I'm just going to erase this. Sorry. Okay. So graphing rational functions. Graphing rational functions. So let's look at this. Let's do an example. X minus 5. Yeah, let's do that one first. So x minus 5, x plus 2, x plus 1, x minus 2. Okay. So you can do some. You can consider some simple things first. So what can we determine about this function? Some simple things are you can figure out the domain and the intercepts. Right. So looking at this function, what's the domain of this function? What are reasonable x to put into this thing, and what are not reasonable x? Okay, that's the better question. What x do not work for this function? -1 and 2, right? And everything else is fine, right? So the domain is the whole line, but not -1 and not 2, right? So the whole real line, excluding those two places, right? Okay. We can think about the x-intercept, right? Where does y equal 0? So I just look at it. Where does y equal to 0? So 5 and -2, right? So just look where the numerator is 0, right? Right. We can figure out, say, the y-intercept, right? So this is where y equals 0, right? And if x is equal to 0, what kind of value do you get out of this? Yes, Dylan?
So that's what I thought you were asking for when I just responded, but I think it would be 5 too, right? Because -10 over -2.
That's true. Okay, sorry. Yeah. So y is going to be 5. Yeah. So yeah, when x is equal to 0, we get -10 over -2, which is 5, right? So what do we know about this guy so far? We know that -1 is no good, right? In fact, we know that that's going to be an asymptote, right? Wherever the denominator is 0 is where you've got an asymptote, right? So we know that there's asymptotes at -1 and 2, we know that the x-intercepts, 3, 4, 5, x-intercepts are at 5 and negative 2. We know it crosses the y-axis at y equals 5, right? And let's see, what else can we do with it? What else can we do with it? Well, we can look at asymptotes. Right? So asymptotes, I guess we've already figured out the vertical ones, so we just need to look at the horizontal asymptotes. So what happens to this as x goes to positive infinity or negative infinity? It's done.
I think that it would tend towards 1.
1, yeah, it's going to tend towards 1 because remember, all you need to think about is the term of highest degree, right? That term of highest degree is going to dominate on the top and on the bottom. So the highest degree term you're going to get on the top is an x squared, right? There's no coefficient on it, right? On the bottom, you're going to get also an x squared, right? So right, as x goes to infinity, this r of x basically turns into x squared over x squared, right? Which becomes 1. Right? And similarly for negative infinity, you just need to look at the top terms. So either way, we know that as you head off towards infinity, the values are going to tend towards the line y equals 1. Okay, so we've got a certain amount of information so far, and what we can do, the last thing we can do is this business of approximating, so getting say, a finer approximation near zeros, and also near the poles. Okay. Do you remember what we did for the polynomials? We were able to get some sort of approximation for the thing near the zeros. You can do the same thing near the poles, right? Because those are kind of things that features of interest of this function. Okay. So right. So our zeros and poles. Let's do the zeros first. X equals -2, x equals 5. We have these poles at x equals -1, and also at x equals 2. Okay. And the game was, just to, so you look at your function. Remember how we did this. Your function looks like that's going to give you 2 squared, which is 4, over 1 minus 3, which is -2. Right? And so we end up with -2 over x minus 1. Right? Okay. And then the last one, right? We factor out the x minus 3 term, and we're left with this thing, x plus 1 quantity squared over x minus 1. And so you plug in 3 into this guy, you get 4 squared, which is 16. You get 3 minus 1, which is 2. And so we end up with 8 over x minus 3. So those are our three, that's what happens near the poles and roots. Okay. So again, we're just gonna use our previous knowledge. We say, okay, At -1, we look like the line y equals 2x shifted over and flipped upside down. Right? At oh no, that's not right. Sorry, that was at 1. That's at 1. So at -1, we look like x plus 1 quantity squared. Right? 1/8 x plus 1 quantity squared. So we look like a parabola, but sloping up like that. Okay. And then over here at 1, we look like this, right? It's a line. Sorry. We look like the 1/x function. We look like the 1/x function, but turned upside down. Right? So we look like the 1/x function, but turned upside down. So it looks like this, like this. Right? And then at 3, we look like the 1/x function. We look like the 1/x function. Right? So we see what's going to happen. It's going to cross over here, and it's going to head up like that. This one is going to come down. It's going to tend towards the asymptote as time goes on. This one's going to tend towards the asymptote, right? This one comes up, this one comes up. There must be some point in the middle where it turns around. So that's what that looks like. Okay, that's it for today. X minus 5, x plus 2, x plus 1, x minus 2. Right? So you take your function and you say, well, let's let x tend towards -2. So really what we're doing in the language of calculus is we're taking a limit of the function as x tends towards the volume. Okay, this is something that you'll see next year or next semester, right? We're letting the x's get really close to -2, and seeing what the function looks like. Okay, well when we do that, right? When we do that, we see that this is going to turn into -7, right? This is going to be -7. We're going to keep that thing because otherwise we get the 0. We're going to have a -1 on the bottom times -3, right? And so we get -7 thirds x plus 2. So really, to be precise, what we're doing is we're taking the limit of these other factors here. Okay, we're leaving this guy alone, and we're taking the limit of the other factors. Okay, so I shouldn't write this because this is a lie. What we're really doing is taking the limit of the function, but taking this term out, right? And that'll give us some constant, right? That'll give us this -7 thirds. Okay, right. We're taking the limit of this thing to use the language of calculus. Okay, is that, you guys okay with that? Why don't you try the next one, just for practice. So x equals 5. What does the r of x is then going to be like what? Yes, Anna?
On that method,
Yeah.
where did the -3 come from?
Did I mess up? This is negative. Oh, thank you. Yeah, it's negative 4. Okay, let's do this one. So as x goes to 5, what are we going to do with this? Yeah, Olivia.
Plug in 5 for all the x's except for the numbers to
Yep. Right. So just hold this one, and we're going to take the limit as x goes to 5 of all these guys. Well, this is going to turn into 7 over 5 times 3. 6 times 3. So just 7 over 18. Right. So that's going to be our coefficient. We get this thing turns into 7/18 times x minus 5. Right. So as x goes to -1, right, you're gonna keep the 1 over x plus 1, and then just evaluate the other guys. Right? So you get -6 times 1 times divided by -3, and so you get twice 2 over x plus 1, 2 over x plus 1, right? And as x goes to 2, right, we're going to get -3 times 4 over 3, everything times 1 over x minus 2, right? And so we get -4 over x minus 2, right? Everybody happy with that? Any questions? If anything's confusing, just say so. The rule of shamelessness. Yeah. I should say that I followed that rule pretty diligently when I was learning Chinese, and it worked. My Chinese became pretty good. Yeah, that actually caused me trouble some years later when I went to Taiwan and spoke to the immigration officials in my my Chinese that I was so proud of, but I sounded like I was from mainland China because what I learned in college was that kind of accent, and so they thought I was from mainland China. They thought I was a mainland Chinese trying to sneak in posing as an American, and I was interrogated for an hour. Yeah, it's pretty funny. I mean, in hindsight, it was funny. At the time, it was kind of fun. But yeah, so I wrote to my college magazine and I said, thanks to the thanks to the excellent instruction of the Princeton Chinese language program, I was stopped as a spy and interrogated for an hour by the Taiwanese immigration officials. Yeah. Anyway, shamelessness. Okay, so what do we have here? Right, we've got all this information about what the thing looks like. This is 4. We've got this thing, we've got this thing, we've got this thing, and we've got this thing, right? And so we use that in all 4 places, right? So here is negative 2, right? And we know that near negative 2, it looks like the function x plus 2, right? So it looks like the function y equals x, but shifted over twice and then flipped over, and it has a slope of almost negative 2. So it looks something like this, right? So we know that there it looks like this. We'll use some color. Sorry. Okay, right. So that's what it looks like there. At 5, right? We know that it looks like again it's the y equals x line, but shifted over 5 units and then given us kind of a half slope, right? So a slope of 7/18, right? So less than a half, something like that, right? Over here, at x equals -1, it looks like the 1/x function, right? This is a transformed 1/x function, right? So it's 1/x shifted to the left and multiplied by 2. Right. So So from here, it's going to look like this, I guess. Looks like the 1/x function, and from down here, it's going to look like this. Right. So it goes up and down like that. Right. And we know that it crosses the axis. We have that y-intercept there, so let's take advantage of that. We can start sort of connecting things together, right? And then this last one at x equals 2, it looks like the 1/x function but flipped over, right? It's multiplied by a negative number, so it's going to go down over here, and it's going to go up over here, right? And it's multiplied by 4. Kind of high up. Okay. Right? And then you can stick, and we know that it tends towards these asymptotes as time goes on, so we can kind of start gluing things together. This is maybe what the function looks like. This gives you a pretty good sense of what the function behaves like. Yeah. Let me have, I was hoping to get to the exponential function today, but I think we probably won't make it. Let's do a couple more examples of this. I'll have you try one. So here's one from the text. X plus 1 quantity squared over x minus 1, x minus 3. Okay, so take a couple minutes to see if that works. See how that looks. So I've just used just for your entertainment, I've just used a graphing calculator to get an actual, more accurate picture of this. And you see, we're not too bad. Okay. Somebody tell me something about what this function looks like. Somebody tell me something about this function. Should I choose people randomly? Maybe I should finally do that. Manuela is you. 1, 2, 3, 4. So I vote 4. Do you want to tell me anything about this function?
So I observed that because of the domain would be and you can mix it for 1 and 3 for x. So if you were to put this into the denominator of the natural function.
Yeah. So 1 and 3 are taboo for this function. We know that there's going to be the vertical asymptotes there. again, remember that we've got this convention that there would be no common factors. Otherwise, we can't so readily say that there'll be asymptotes there. Okay, would somebody like to say something else, or should I call on people randomly? Yes, sir.
There would be a horizontal asymptote at 1, right?
Mm-hmm. Horizontal asymptote at y equals 1, right? Because again, the term of highest degree on the top is x squared, and the term of highest degree on the bottom is also x squared. So we have the same situation, right? We know that this line at 1 is going to be a horizontal asymptote. Okay. What else? Yeah, still.
X-intercept at
X-intercept at, right, so we get 1 over,
what? I think
Ye-
the y-intercept would be 1 over 3, right?
the y-intercept is going to be 1 over 3. Yep. So we know that it's going to cross over here. Right. And then the x-intercept are at 1, wait, the x-intercept is negative 1. Yep, thank you. Okay, so you can get the intercepts, and then the last part is this business of doing the approximations, right? So, right, we have this root at x equals -1. We have a pole at x equals 1, and also at x equals 3. Right. Right. So, does somebody want to tell me about this first one? What does it look like near x equals -1? I'll just call people. Sorry. How many people in the class? 7, 8. Jocelyn, do you want to do this one?
I'm kind of confused. I'm trying to like
Okay.
figure it out.
Yeah. So the way you do this sort of thing is you say, well, this when x is -1, right? We've got this term. This is the term that gives us the x equals -1, right? So we take that term out. Okay. We hold that term on the side, and we take the limit as x goes to -1 of this other thing. So right, so we've got x -1, x -3 like this, and so we rewrite this like this, and then we evaluate this thing at -1.
Wait, how did you get the 1 on top?
So this is the same thing as x plus 1 squared times 1 over x minus 1, x minus 3, right? So that's all I've written here. I've just written the x plus 1 over here, and the 1 over x minus 1, x minus 3 over here. Right? So this one is just from you factored out this the numerator, right? It's just like right, if I write a over b, I could write it as a times 1 over b. Right? That's all I'm doing. Okay. So then what you do is you let x go to -1. Well, when x goes to -1, this thing becomes -2. Right? What happens to this thing? Well, if x is -1, this factor is going to be a -4. Right?
So every time you're solving, you need to factor it out, or like expand it.
What you do is you separate it. You separate it into the part that gives you the root, and then the rest of it. Okay. So right, in this case, this thing is the thing that gives you the root. So you just move that out, and then you evaluate the rest of it. Right. So this is going to give us 1/8 of x plus 1 quantity squared. Okay. For this guy, For this guy, this is the term that we're concerned with, right? So we've got this 1 over x minus 1, and then everything else is, this is the other part of it. This is the other part of it. That's the part that's gonna give us our coefficient, right? So you just substitute the x equals 1 into there, right? And that is gonna give you